Hi there, Mr. Sutton, bringing you the Pre-Cal Honors 4-7 Extra Practice Number 2 solutions on applications of exponential equations. For this problem, we have a $10,000 certificate of deposit at a bank growing 8% each year. That's a pretty good deal. How long does it take for this money to triple in value? All right, so since we're growing 8% only every year, we're not really compounding more than once a year, I'm just going to use my PB to the T formula here. F of T equals that. And we want to know how long, so we're solving for T in this setup. So that means I have to plug in stuff for the other three unknowns. F of T is what we want this to grow to. Not really sure. Well, actually, it says triple. So 10,000, if we triple that, is going to be 30,000. There we go. And then P, that's what we're starting with. That's the 10,000. B value, what I'm multiplying by each year. Since I'm growing 8% a year, I'm multiplying by 1.08. And then T, we're solving for that. So let's isolate that exponential term, and then we can use logs later on. So divide both sides by 10,000. That's going to be just 3 on the left side. Now if I take the log of both sides, I have log of 3 equals T log of 1.08. And now that I've popped T out of exponent land, I can actually solve for it. All I have to do at this point is divide by log of 1.08, and now I'll just plug that into the calculator. So it looks like this is going to give us a value of about 14.27, so that's in years. That's how long it'll take to triple our investment. On this problem, we have a radioactive isotope with a half-life of 9.6 hours. We've got 1 kilogram now. How long will it take to decay to 1 gram? So since we're doing half-life, let's use the half-life formula. That's going to be F of T equals AB to the T over K. And we're solving for T because we're asking how long. So we need to plug in things for all the other values here. F of T, that's going to be how much is left. So there's different units. We've got kilograms versus grams, and you're going to have to make a decision. I'm going to go ahead and use 0.001 for my target value because I'm going to express this in terms of kilograms. I could have used 1 here, and then my A value would have been 1,000, but I kind of like using 1 for my A value, 1 kilogram, 1 starting amount of stuff, because 1 is a lot easier to work with. I guess you'd have a 1 over here, so that's not too bad to work with, but whatever. Just pick 1 and go with it. So then our B value is going to have to be 1/2 because we're dealing with half-life. T is what we're solving for. K, that's our actual half-life, so we're dividing by 9.6. And now isolating the exponential term, well, it's already kind of isolated. 1 is not going to change anything if I'm multiplying by that. So I can go ahead and take the log of both sides to pop out this exponent. I've got log of 0.001 equals 9, or T over 9.6, log of 0.5. And at this point, it's just a matter of isolating T. I can do that by multiplying by 9.6 times log of 0.001, which, yes, I know that's really -3 because this is log base 10, but there's no need to really write that if I'm going to do it all on the calculator anyway. Next, let me divide by log of 0.5. And now let's see what the calculator has to say about this. Plugging all of that in gives me a time value of about 95.67. Since my half-life was in hours, this is 95.67 hours. For this problem, we have the isotope berkelium-247 decaying at a rate of 50.23 per thousand years. So that's almost the half-life they're giving us, but not quite, so it'll be a little bit off if you just try to do standard half-life. Current mass is 100.1 milligrams. In how many years will this diminish to 22.2? All right, so this is a half-life kind of situation, even if it's not true half-life, because this decay rate is happening over every certain amount of years. It's not happening every year. It's happening every 1,000 years. So I'm going to go ahead and use the half-life formula. So that's going to be AB to the T over K. Since I'm solving for in how many years, I'm solving for T, so I need to plug in something for all the other values. F of T is how much is left over. That's this 22.2 milligrams. A is the 100.1 milligrams we're starting with. B is not 1/2 because we're not multiplying by 1/2 every 1,000 years. we're decaying by 50.23%. So we're multiplying by whatever 1 minus this is. I'm going to do that on the calculator. So on my calculator, I'm doing 1 minus 0.5023, giving me a growth factor of 0.4977. So we're essentially keeping 49.77% of this stuff every 1,000 years. Okay, so then we have to raise that to the t over k. T, we're just going to leave as t because that's what we're solving for. K is the 1,000 years we have to wait before multiplying by a full one of these percentages. So now let's go ahead and solve for t. I can start by dividing by 100.1 to isolate the exponential term. Next, I'm going to take the log of both sides to pop that exponent out. So I've got log of stuff on the left equals t over 1,000 log of 0.4977. At this point, we isolate t. I'm going to multiply by 1,000. That'll go with this log of fraction stuff over here. And then I'm going to divide by the log of 0.4977. So that goes down below. And now it's up to the calculator. So what does all this come out to now once we enter all that craziness in there? That's going to give us about 2,158.45, and that's going to be in years because the half-life was in years. On this problem, we have atmospheric pressure decreasing approximately exponentially as elevation increases. Rate of decrease is 12.5% per kilometer. Pressure at sea level is 764 millimeters of mercury, if you don't know what that means. And at what elevation is the pressure? 440.8. Okay, so we have, let's see, this is kind of a weird situation. There's no time involved at all in here, but you can think of elevation as time. If you think about it as input versus output, you're telling us the elevation, and we're telling you what the pressure is at that elevation. So as the elevation increases, or actually the pressure decreases as the elevation increases. So the rate of decrease is this. We want to know at what elevation do I need to go from 764 to 440.8 milligrams of mercury. So I'm going to use the standard exponential formula on this one because I don't have to wait a certain number of kilometers. This is a rate of decrease per kilometer. So I'm just going to use f of t equals ab to the t, and I'll figure out what to plug in at this point. So I'm solving for t, but t isn't really time in this case. It's elevation. It's an input that I'm solving for. So I'm going to have to plug in things for everything except t, and then I'll solve for t. F of t, that is f of t and a. Those are both my pressure. F of t is what my pressure becomes. So they're saying at what elevation is the pressure? 440.8. So that's going to be our F of t. That's our target pressure. A is the pressure we're starting with. That's going to be 764.0. B is what I have to multiply by each time I increase that pressure. So if we're decreasing 12.5%, that means we have to subtract 0.125 from 1. And you could use a calculator, but it's about 0.875. I happen to know that one in my head. And then we'll have to raise that to the t. We don't know what t is yet. We're solving for that. Now to solve for t, I have to isolate this exponential term. Let me divide by 764. And then I have to take the log of both sides. So we have log of the left side equals t log of 0.875. Pop-out rule there. Next, to get t by itself, let me divide by log of 0.875. So I've got all of this stuff divided by log of that. And then let me plug this in the calculator. So if we plug all of that in, and we're careful with our fractions, that should come out to about 4.12. Now, what unit should that be? Well, they said at what elevation? Elevation was the input that we were solving for. So the elevation is measured in kilometers. So that's going to be 4.12 kilometers.